My name is Ko, and today we are going to present you everything about green software engineering. The most important question is, what's in it for you? We are going to learn you, or I hope you will learn some principles of green software engineering, and we're giving you some practical tips on your application, on your GVM, code guidelines, architecture, and web frontend. And I hope you will enjoy. So the first question is why? Why are we doing this? Why should you take care of green software engineering? And I have a 3-minute video here about from the European Union, and then you know why you should take care of green software engineering.
This is you. This is our homes, our cities, our lives and livelihoods. And this is climate change. It's here. It's happening right now. People sometimes wonder, what will happen in Europe if we do nothing, if we let global warming continue? Each year, an additional 15 million people will be exposed to high wildfire danger. Heat waves will cause 90,000 more deaths every year than now. Over 2 million more people will be flooded in coastal areas and river floodplains, while annual flood damages will rise to 300 billion euros. There will be major shifts in ecological domains throughout Europe, with alpine tundra seriously contracting and almost disappearing in the Pyrenees. Droughts and water shortages will impact southern regions even more than they do now, affecting farming, crop yield, energy production, and public water supply. What will happen if we act? If we limit global warming to well below 2 degrees, how will people, the economy, and ecosystems in Europe benefit? 2/3 of the increase in people exposed to high wildfire danger would be avoided. 2/3 of the increase in deaths from heat waves would be avoided. The impacts of coastal and river flooding would be more than halved, and stress on ecosystems and habitats would be considerably lower. The drop in water resources availability and drought losses in southern regions would be halved. And if we also adapt to climate change, we can reduce impacts even further. Adaptation can have long-lasting benefits for our people, economy, and our ecosystems. Our study illuminates the importance of the European Green Deal, putting climate action at the heart of our long-term strategy, and why Europe is committed to be climate neutral by 2050.
So, yeah, that was pretty heavy, right? And yeah, that is our reason to think about things we can do ourselves, like the small things that can help us. And we can also do this in green or in our own landscape. So, yeah, my name is Turk. I'm a developer working for Blue for IT, part of Adesso. I'm a speaker, assignment at the Rabobank, writing blogs, and I'm not perfect, so I was coming with a car, but I believe in innovation. And innovation means like we're going with electric cars and we're going to innovate, so I believe in innovation there. I'm not perfect.
Thanks. My name is Ionut Balosin. I came from Vienna, from Austria. I worked there as a software architect for Raiffeisen Bank International. It's a pretty big bank over there. And I do a lot of other things besides the job on daily basis. I do trainings, I talk to conferences, I write blogs and all of these things.
So yeah, we have the slides here already and GitHub. We have already did some studies, so we also show you at the end. But yeah, maybe I make some pictures. Good. So the story: more than 2% of global CO2 emissions we spend on running our application. So on every layer we can do something. So when we are taking our mobile or creating our application, or we can code differently. All that kind of tiny things that really matters. And if you compare it, the IT industry is almost the same like the aviation industry if you look to pollution. So we can do something here. Yeah, first some philosophy, and then later on we will continue to the practical stuff. Yeah, we are part in this together, and there are 8 principles of green software engineering. 1, we need to create, we need to carbon efficient. We need to be energy efficient. We need to think about solar panels and that kind of things. Hardware needs to be good. We need to be efficient, like going to the cloud, serverless. Less connections is better. We need to think about running our application at certain times. So when we have solar panels, they are active, or we need to monitor and measure our applications. So that's in a nutshell what the principles are, and we're now going to do the interesting stuff in my part. So we are going to continue with, it's all beginning with your Java virtual machine. Ionut will tell you something about that later on, some code guidelines, architecture and web frontend. So I give you the clicker.
Yes, thanks. So what's the purpose of this chapter? We have to understand that, or what we try to understand, that even keeping the same code just to changing the JVM itself can have an impact. Therefore, we did a bunch of measurements. We really measured the energy consumption under specific test cases. And within this Java Virtual Machine subchapter, I will try to share those with you. But before going into really the measurements themselves, I'll try to explain a bit how we conducted that measurements. The problem is today, the software industry do not offer us so many possibilities. Therefore, we did those measurements on Linux, and in particular just for the Intel chipset. Why is this? Is because Intel has offers, the Intel chipset offers the interface called RAPL. You have it there on the bottom of this. It stands for Running Average Power Limit. What is this? This is an interface so you can read, for example, from some CPU registers that are refreshed or updated with a specific frequency. You can read how much energy was consumed. Of course, this REPL, because it's an interface and it's bound to the CPU, it was not primarily added by Intel to measure the energy for us, to understand how green we are. The initial purpose was actually for some internal management of the CPU. One of these is, for example, to understand how much power consumption the CPU has when the turbo boost is enabled. So effectively, they try to, they added these registers in the CPU for some internal management of the system on chip. But nowadays, people are using this to measure the energy consumption. Nevertheless, it comes with mainly 2 limitations, the most important ones. First of all, it measures, because it's bound in the CPU, if your application does some intensive I/O, either disk or network operations, you cannot read the energy for those I/O operations with REPL, because REPL, it's in essence, it measures the CPU plus the memory. So it doesn't measure outside of CPU and memory. Therefore, in our experiment, we try to keep the applications either CPU intensive, either memory intensive. That's one part. And the second limitation, or it's not really a limitation, it comes implicitly because it's bound in the CPU. If you have on the same host multiple applications running, of course you measure the energy consumption for all of those applications. So therefore, it's very important to understand what's your baseline. So for example, for us, we took a baseline when the system was idle, up and running without any load. We measured that a few times, and then we started our JVM, and then we try from the JVM measurements to exclude the baseline, because otherwise you will say, okay, it took like, I don't know, 100 joules or watt second, but for example, 30% of this is just the baseline of your operating system. Now, this is important thing to consider, and we took, because it's very simple, you just keep the same code, we took a bunch of JVMs, all are listed in this slide. Therefore, I will show you how it goes. In particular, this is a slide which explains how you can, for example, calculate the energy consumption using the REPL interface. The REPL interface has, it gives you the energy for the package. You see the package, it includes all the cores that you have on your CPU, plus, for example, the integrated graphics. And that one, it's one stat. And we sum it up with the energy for the RAM. Therefore, our measurements were based on this formula: the energy for the package, which includes all the cores plus potentially integrated graphics plus the RAM. And how we did it? Yeah, I will try to. We used perf for that, and for this perf. What we had, we started the perf command. Yeah, so you see it here actually. Is it visible, or the font is too slow? Yeah, is good. Yeah, good. So how we did it? Every time when we try a measurement, we started the process itself with a perf command, and we tell perf to give me when the process finishes, to give me the stats, the stats being these events which are related to the energy consumption. Therefore, we took those stats that perf reported, and then we sum it up. And we did these measurements multiple times, and then we came up with some analysis on the data, and we plotted this data. So this was, in a nutshell, this was our methodology. And more things on this. Let me show, where is the slide? Yeah, presenter. Yeah, maybe this one. Yeah, good. And so this was the methodology. Now we took I'll present now some custom off-the-shelf applications. So therefore, these applications are applications that you just grab it from the internet. We didn't code anything. And we just try to measure how much energy those applications consumes. This is a very important thing to what we did. We were careful, because just running an application without any load, it doesn't mean too much. You need to have a good enough load test to trigger all the endpoints from your application for a sufficient time interval. Because otherwise, if you just start the application in idle, it doesn't consume anything. It's not relevant. Therefore, what we did, the first application is the Spring Boot Pet Clinic. Have you heard about this one? Yeah, it's very famous. What we did, we took this application and we created a test scenario. The test scenario, it's defined here. I wouldn't go too much into details on this. In a nutshell, this application, it's a web-based one which exposes multiple endpoints. So for example, you can search for pets, you can add pets visit, you can do a lot of things. And we used load test tool, which is called Hyperfoil. Have you heard about Hyperfoil? Have you heard about Yeah, good, very good. Have you heard about WRK? Vereka, yeah, very good. So this tool is very good because it doesn't fall into this coordinated omission problem. So it's, in a nutshell, it's very accurate in comparison to other tools. So therefore, we took it, we created, we defined in DSL, we defined these test cases. We started the JVM with perf command. We said to the JVM to monitor the energy for that one, and we actually, during this interval, we triggered the load test. I admit it was not a heavy load test because, as it's written here, I think, Yeah, in total, during this execution, in terms of time, it was 15 minutes, but the total number of requests triggered during the application startup time, running time, were like 110,000 requests. So as you can see, it's not a lot. The running period was not very long, yeah, but for us it was just good enough to have an understanding. And this is the graph that we had. Sorry, where internet it's not working. Yeah. I hope it's still good enough for you. This is a bar chart, and each of these lines or each of these bars represents the energy consumed. Of course, if the bar is shorter, which means more, it's better, it's more eco-friendly. And here on the vertical axis, you have all of the JVMs that we tested. Yeah? In a nutshell, what we can say out of this test is just by switching, or for example, going and compile natively with native image, this was the best test case. So this saves us a lot of energy. It's actually closer to Oracle Graal VM if you see here. So the orange one, you can see here the legend. The orange it's Oracle Graal. The light blue, I'm not very good with colors, it's OpenJDK. The magenta or pink, it's native image. The next one, it's Graal CE Community Edition. The next one, it's Oracle J9, and the last one, it's Azure Prime. So these were the results of out of our measurements. One very, very important: don't mix performance with energy consumption. Yeah? So during this talk, we are not associating at all performance with energy consumption. Of course, in some cases, it might be a direct dependency, but based on what we observe, it has nothing to do. I mean, telling that it's less energy efficient, it's less performant, it's false. Yeah. The other way, it's not also true always. Telling that it's more eco-friendly, it's more performant, it's also not true always. So therefore, don't associate these results with, okay, that the JVM was less performant. No, this is a JVM energy consumption talk. Yeah? For performance, there is a different set of concerns and measurements. So this was the first case with Spring Pet Clinic. The second test case was with this, I found it, with this, so this was the Spring Pet Clinic. We said, okay, we took something from, based on Spring, therefore let's take something from Quarkus. Yeah, these are probably very well-known frameworks. Nevertheless, the idea, we cannot compare between Spring and Quarkus. This was not our intention because the code is different. You cannot compare a Quarkus application with a Spring application. Unless you really have the same code, the same jars, everything should be the same. Yeah? But what we try to say is that we change from one type of application to a different type of application, using a different technology stack, and we measure the energy consumption from a JVM perspective, but not from the framework perspective. Okay, so this was about Quarkus, and Quarkus provides a lot of samples. So this comes, for example, with SAM. We explicitly took this Hibernate or Empanache. It's a Hello World application, but in a nutshell, it's microservice which exposes some endpoints. These endpoints are in a nutshell to create, it's a CRUD operator. It allows you to do CRUD operations. And what we did, we triggered request with a specific load during, again, 15 minutes for the time that the JVM was running. In total, there were like 650,000 requests. And this was the results that we came up with. one important aspect which I didn't mention, to end up with these results, we measured multiple times. So we didn't start only once. We didn't trigger only once the measurements. We triggered measurements multiple times, the same test, and then we calculated the normalized geometric mean, the geometric mean, sorry, and not the mean itself, because if you have multiple results and those results are very different, the mean, it's not useful. It more confuses you. But the geometric mean, it's a way that tells you where are the majority of those results. I mean the tendency of your results. Therefore, we use this formula, which is geometric mean, to plot these results. So these numbers, the energy consumption numbers, are the geometric mean numbers out of some a lot of repeatedness measurements. Also in this case, native image was, it performed quite good. Then you can see, you can judge by yourself based on the length of these bar charts, which one is, a bit more efficient or which one is not so efficient. And this was the second use case. The third use case was, we said, okay, we took some web-based frameworks, but let's take something which has a bunch of tests, and therefore we thought about, let's take Renaissance. Have you heard about Renaissance? Yeah? What it is, Renaissance, it's like a bundle of test cases. It's a performance test cases. They are clustered in different categories. So for example, in Renaissance, you have for concurrency, you have a bunch of tests. For functional, but they are very specific on functional, you have a bunch of tests. For Scala, you have a bunch of tests. So they are very much different, yeah? Concurrent, functional, Scala. And we took that, this is like a jar, and we tried to measure, yeah, how much time it consumes each of these JVM to run this Renaissance benchmark suite for different categories. And here, actually, we took 4 of these categories, concurrency, functional, Scala, and web. In comparison with the previous, the Quarkus and Spring, that were running like 50 minutes, these, I would say, they are long-lasting applications, because each of them ran for at least 1 hour. For example, the concurrency, if I still remember, took like 5 hours to run. So it's really a lot. And we measured the energy consumption during all of this period. And yeah, as you can see here, also we got different results. For example, which, let's take here, the Renaissance functional, the Azure Prime was very good, but it really much depends from case to case. You cannot conclude that one JVM is always better. It really much depends. What is the important thing, and what would like to transmit is, we set a benchmark and a methodology for you to assess and to understand how much energy you consume in some cases, because each application is different. So we cannot say actually that use that JVM because the JVM it's the best one. Yeah. Therefore, my message is, of course, don't rely on my measurements, first of all, but I want to tell you how we did it. I want to get a very tangible way of how you can do it on your project, because this is, I think, what it's important. We found on the market a lot of articles, very, very theoretical, but we try to make a bit of pragmatic approach. So therefore, this is one of the approaches that you can take it away and measure your stuff, and you have to decide for yourself which JVM is the most eco-friendly in comparison with some real load. Yeah, you have to trigger the load, keep it running for 8 hours, for example, and then you conclude. And that actually ends my part, and I'll pass it to Ko to go into some code lines,
nice.
Guidelines. Sorry.
Perfect. Thank you. yeah, it was interesting to see like GraalVM was really doing good here. Native image, right? In our case, so that was really great to see. So who's using Sonar here? Nice, nice. So some pragmatical things like there is an open source plugin available for you that you can use. It's called Eco Sonar. And you can just use it and run it against your own code base. And that's pretty interesting because it's a kind of rule set you can use and it's giving you some tips like, hey, maybe you should do this differently. So if we look to this one. So I was taking your application, Ionut, surprise.
It's a good surprise, yeah.
So yeah, you have an e-commerce application. I was thinking, hey, let's measure it. How eco-friendly is it? So I'm running a local instance and it should be doing something. You expect, of course, not.
Does it depend on the internet because you don't have?
Maybe, I didn't expect it, okay. I hope this one will work. Just local, so okay, nice. Dashboard, just checking my local instance is running. It's just a Docker container, Sonar Cube, so you can, okay.
That's the beauty of live demos. Everything works, but when you have to do it, it crashes.
Embedded gateway should be used for, okay, we will. Okay, now, but what this does is, I'm going back to the presentation, and it's pretty cool. It's having a rule set. So it's checking your code. It actually checked your code, and it saw already a bunch of things. These are the Eco Sonar rules. Some are maybe not so important, but these are the rules that are important, or yeah, can be important if you do it a lot of. If you have a lot of violation of that, it will help to reduce your CPU, help to reduce memory. Small steps, but it can help your code to be more friendly. So this was one thing. And you can also use it in your pipeline, right? So now you can just run it in your pipeline and yeah, it just runs. And I think it's working nicely. Yeah, some patterns still for you.
Yes. Yeah, thanks. Previously, I've told you about the, how you can just switch or jump from a JVM to another and see that it really makes a difference. But then we thought, okay, let's make it a bit more hands-on. I mean, for me as a programmer, I probably don't have always the choice or the power to decide what JVM I have to use in production. Yeah? There might be some very strict rules from company to company. Yeah? You might need some licenses for some of the JVMs. And therefore, we try to complement with some patterns. And we thought, okay, what are the most common patterns that each developer knows or uses? Yeah? So we have 5 of them. I included here only 3, but the 4th and the 5th one are in the article, so you can read them afterwards. Or if we have time, because the demo was somehow cancelled, we can also go into this. The first one is about memory. Yeah, what it is about. When we create and instantiate some data structures, like for example arrays or whatever, and then the thing is when we read the data from that data structure, what happens? Because the objects, all the objects are allocated in heap, right? And to be able to hit those objects from the heap, they need to be fetched from the memory and they need to be added to the CPU cache. This is how it works. This is how it works from hardware perspective. And how this is done, for example, if something is requested, and if it is not in the cache L1, L2, L3, it is fetched from the main memory and put it into a CPU cache line. And the way how, for example, this is how hardware it's built. One cache line is fixed. Yeah, you cannot have one cache line infinite in size. In most of the in most of the architectures, one cache line is 64 bytes. So every time when CPU reads something from the main memory, it adds 64 bytes. And for example, even if you need 2 bytes, which are not in the CPU cache, 64 bytes are added, because the way how CPU sees the main memory, it's in CPU cache line sizes. Okay, so this is a bit of context. Now what we did, based on this, you can understand that if you access, for example, if you have an array, and this, let's maybe open, but we don't have, we have internet, which it's good. What I've created here an array of, I allocated an array of longs of 4 gigabytes, so it's really a big one. And I try to understand what is the impact on just accessing the array elements while I was requesting elements in 3 fashion. Or yeah, the first one is I was just iterating through the array with a very predictable pattern. So for example, I have a counted loop, and then I increment the stride by 1, the counter itself, ++. And this is very good because you request one element, and implicitly the next elements, if they are co-located in the main memory, they are all fetched and in the same CPU cache line. So this is very good because then when you read the second one, it's already fetched. And more than that, because this is a predictable pattern, the CPU will prefetch for you the next element, so you don't pay the cost of CPU cache misses anymore. And therefore, you have it here as a very, very good and the most optimal also from energy consumption perspective. So it's not, here I would say is the same performance-wise, but it's also from energy consumption, it's much more efficient. And then we have also 2 other ways. Two other bets of accessing memory. One, it's about data locality, and the other one, it's about temporality of the data, which means data locality, if I request something, it's likely that the object that was co-located, I will request it in the next, for example, cycle, because it's co-located and maybe it's already in the CPU cache. And the same for temporality, which means the data that I requested before, it's likely that I will request it again. It's still in the same. It's still in the CPU cache. And we did this. We try to access elements out of those array into a very random order. So we just created random indexes accesses across the full 4 gigabytes, and therefore you can see how much energy, how much less efficient it is. Because of course the CPU has to do more work. There are more cycles to fetch the elements, put them in the CPU cache, then evict those from the cache, and so on and so forth. And we also tried something intermediate. Let's say we clustered the elements, the full set of elements in pages. Not 4K, but in our case was 2 megabytes, and then we try to randomly access elements from in that area. And also this was much more less energy consume less energy in comparison to this case, which is the less optimal. But what is the idea? What is the conclusion out of this? The way the memory is laid out, the objects are laid out in a memory, and the way we request those objects, of course, they have an impact on the energy consumption. In a nutshell, if you choose data structures that are more compact and you can iterate or access elements in a more predictable fashion, this also reduces the energy which is consumed. Yeah? So when you choose some data structure, think also about this, because of course the CPU has to do more work, more CPU cycles, more energy is consumed. This was about the memory. About logging, we all use logs. Yeah? The problem with logs is when you log, you create the library itself. It creates a lot of garbage, and when something gets logged, and of course this impacts and adds more garbage collector cycles. But it also impacts the I/O, because you always log. So you have an I/O intensive operation if you log continuously. And what we did, we tried actually to take some logging patterns. These logging patterns I will explain briefly.
Is it visible for everybody to see it, by the way?
Yeah.
Maybe we can enlarge it a little bit? Or?
Yes, please. Yeah. Or the light, yeah. Okay, maybe.
How can I light this? Is there a light mode somewhere in settings? Does someone know?
You can search for
settings or something. Light.
No. This is Chrome. No, sorry, it's good.
Yeah, oh, it was good.
It's
okay.
Good. Yeah, it was good. I thought it's the ED.
Light.
Appearance. You see it here.
Okay, appearance. Team.
Chrome just uses the setting you have on macOS.
Okay, yeah, we try to
just make it a bit bigger, and yeah.
Which one was it? Was it this one?
Yeah, it was here. Yeah, very good. Even a bit, I would say.
It's a good one.
Yeah, good. So we try to measure different logging patterns and how they impact the energy consumption as well. Therefore, we just took the use case of string format. It's actually a string.format. It's very simple, and we say logger.log. Then we used lambda expression for this. So this is the lambda body, and inside this lambda body, it's called lambda heap because all of these objects are global variables. And we had a different use case called lambda local, which is logger.log, the level of the log, and this is the body of the lambda, and this time are local variables. And then what we have guarded parameterized logger. What it is, we put first a guard if that logger is enabled, which means if that logger has the appropriate level, we just log it using a parameterized pattern, like this curly brackets 0, 1, 2, 3, 4. And then so on and so forth. Guarded unparameterized does the same. Logger, this is the guard, and this is unparameterized. This is just a string concatenation. Unguarded parameterized is you don't have a guard, but you have this parameterized stuff, and you have it unguarded and unparameterized. So we did this test, but now you might think, yeah, but you told us in the beginning that REPL do not measure I/O. And how did you measure logging? Because logging, it's an I/O operation, correct? Something it's fishy, yeah? It's either what we measured is not true, or we use something else. We actually use the null output stream. So we configured in this test the null output stream. I think I will find it somewhere, yeah? So we configured the null output stream here. You can see this is the output stream.null output stream, which actually doesn't write anything on disk. Because otherwise, if you have this, and this was really an intensive I/O, disk I/O test, you will not catch it correctly. Therefore, we just simulated with this null output stream. So this was the test case, and these were the measurements. Yeah. In a nutshell, we cannot conclude something here, which pattern is better. I can see that the string format one, maybe I will also, I think this is better, the string format one, or the lambda local one, the lambda heap, this guarded and parameterized, this showed a bit more efficient. Yeah? You can also see that because we did it with different JVMs, you can see color-based which of those was better. Yeah? This pink one, it's the native image, so this was of course the best one, because this is like a very short running use case. It ran for a few minutes actually, and of course for this short lived running application, the GraalVM, it's a winner here, unless you do some extra tricks for other JVMs, which are available, by the way. So this was one which was also interesting for us. It really much depends, but we can take or make some conclusions based on this. And the last one in this regard was throwing exceptions. Yeah? Do you throw exceptions in your code? No, of course, nobody. Yeah? The throwing exceptions, it's also very problematic. The thing is, it impacts a lot the energy consumption. I will explain what happens in here. When you throw exceptions, depending on the stack depth that the exception is thrown, which means, for example, if I have a method and call 10,000 methods and I throw exception from that point, it's a very much different than I'm just having a method without calling those 10,000 methods and I throw the exception. The thing is, every time when you throw an exception, you need to fill in the stack trace. And of course, if the stack trace is bigger, it allocates more elements and more time it's needed to create the exception before it is thrown, because then you can just iterate and see the full stack trace. And this is what we did. We measure it in 3 different aspects. We say, okay, let's iterate. This is a recursive method until we reach a depth, and then we throw a constant exception. Constant exception, it's an exception that you, for example, declare it like this one. Yeah? You declare a new runtime exception and you reuse it. We also use a supplier, Lambda supplier for this, so therefore we just say new exception. But we also had 2 more cases, like when you throw an exception, it's just throw new, like the majority of us are doing, or filling in by overriding filling in stack trace, sorry. And this is actually a very big gainer in case you don't need the stack traces. Why is that? Because even if you see how much energy you consume, override filling stack trace was much more efficient, yeah, in regards to throwing a exception like just throw new runtime exception. Yeah? For the Lambda one, it's pretty much the same, but also it's good if you declare the exception as a constant one. So this also saves you. So the takeaway from here is, if you really have to throw a lot of exceptions and you have like some, you are an eco-friendly software engineer, think of this, yeah, because this all impacts your energy consumption. Good, and let's move further, because we still have some more interesting things to share, and I will pass it over to my colleague, yeah?
Co-speaker.
Co-speaker, yeah.
So Java is an eco-friendly choice. If you look at some studies, they are like 4th now, or if you look at eco-efficiency. So Java is a good choice here. There are maybe better choice, but Java is really there, and it's going good, I think. And there's also something pretty interesting, and I wanted to share it with you. Who is using Maven caching nowadays? 1, 2, nice. This will be a nice tip, because it's really improving your build time. I will share something like, just escaping here. Yeah, normally what we're doing is like, yeah, Maven clean package. I'm now skipping a test. This is the Spring Pet Clinic. and you can see like, yeah, it's going to build, and you see it's like 6 seconds. And it's only the build, without the test and that kind of things. But if you go to your IDE, you can see you can also implement something like something like this, yeah. And you can add an extension here. It's called the Maven Build Cache extension, and that will reduce your build time. If you change something, it will see, hey, I don't need to build everything, and you need to have the latest Maven 3.9.4 or something, then you're good. And then it's already some quicker. Let's see. So it was 6 seconds and it was 1 second. So it already seeing like, hey, you didn't change a lot, only a POM, and you're already quicker. So this is the tip of the day. And yeah, it helps my life because we have a big repo, and it takes like a couple of minutes to build your project, and that's really annoying that you need to wait. Yeah, it's nice to get some coffee, of course, but yeah, every time building, it's like a lot of coffee, and then you're like, ah. So yeah, so that's one tip what I wanted to share. And yeah, what I said, you can also use it in your pipeline. So there are some caching service you can use then. There's a great talk about it later on. It's from Justin, and it's how to speeding up your Jenkins, Gradle, and Maven with a build cache. So this was just yeah, how do you say it? A detail, a teaser indeed. And yeah, he can tell you more about. So it's pretty interesting, and it can improve your developer life, I think, and developer happiness. What also can help is autoscaling. Who is using autoscaling here? Do we know that? Who has no idea? Still, okay, some. So yeah, that's pretty nice because by autoscaling, you can say like, hey, if the limit is reached, then scale me up another node. And you can do this with Kubernetes, some configurations, some YAML, and then it's autoscaling. So it's beginning with one node, and then it's scaling up with a second node if it's needed. And normally there are a lot of nodes already active, and that's being useless, and that's like a waste of energy. So you can already improve there. You can also go for CF. There are some examples there. Yeah, throw away the garbage you don't need. For example, don't use Kafka if you don't really need it. There are streaming solutions also that are cheaper if you look to the energy. And then go to the web front end. There are pretty interesting stuff like website Carbon. So let's website Carbon. Is it working? Nice. So yeah, we can do different things. Like we can measure, for example, JFall, and let's measure if they are energy efficient. So let's see. And then you can see that they can also improve something. Yeah, most of the websites are like this. Everybody can improve something. You can compress images and that kind of things. You can also think about like, what kind of energy am I running? So what you can do is also, do I have it here open? Like check the greenwebfoundation.org, and you have a list with green hosting companies. And like if you go to the Netherlands, you can see all kind of, oh, this is Belgium. Yeah, you can choose, and then they are green, so they're running on green energy. But there are also like other companies that's doing it also pretty good, I think. I'm working at, yeah, we can, yeah, I'm using now Rabobank. I have an assignment there. And mostly people are like, oh, yeah, the sustainability, there are a lot of problem, Extension Rebellion and that type of things, but inside the Rabobank, they're doing a great stuff there. They're trying to be more sustainable also. And if you look at the website there, it's pretty good, and they also use sustainable energy. So we are getting there. We are not there yet, I think, with a lot of companies, but we can improve there. And this is a way to measure your website. So yeah, check. Thank you. We have. Oh, this was almost the end. Okay, nice. So this was a short demo. Improvements. You can check your images, check your videos, check your content. You can minify, compress your data, and that kind of things. Coding, avoid network calls. And what to remember after this talk? Choose appropriate your GVM.
Before to choose it, measure it.
Indeed.
Don't choose it without measurements. Don't trust anybody. Do your own measurements.
Yeah, do your own research.
Yeah.
Implement Ecosona in your code. Check if it's sustainable enough, if you can improve it. You can do some pipeline enhancements like Maven caching. Do it, like everybody should do it now, next morning or something. And measure your front end with Carbon Calculator. And that concludes our presentation. Yeah. Cool. Thank you.